Alright, hello everyone. In this video, I'm going to be taking a look at the free response questions for practice test number 1 in the folder that I gave you before spring break. So I'm going to be going over the general procedures and thought processes involved in solving these problems, and also let you know how many points each part of the question was worth so you can get an idea of how they were scored. Alright, so to start off with, I'm going to look at question number 1. This is one where we had two blocks on an air track, block A and B. One of them had a spring attached to it. And right here, we're looking at a series of marks that give the location of cart A at various points in time spaced by 0.1 seconds. So the first part of this question, part A, asks you to find the average speed for three different time intervals. So part 1, we're looking for the average speed between 0.1 and 0.3 seconds. So it would be between these 2 points here. So the average speed is going to be the displacement divided by time. So this thing goes ends at 0.3 meters, it starts at 0.1, so take final minus initial position, and the time values are also going to be 0.3 and 0.1, so that gives us 1 meter per second for the first interval. For part 2, we're looking at 0.9 to 1.1 seconds, so that would be this interval right here. Alright, so at 0.9 seconds, we're over here at, it looks like 0.87 meters. And at 1.1 seconds, we are at 0.99 meters. Alright, so if we calculate our displacement, it'll be 0.99 minus 0.87, and then the time interval will be 1.1 minus 0.9. So that gives you 0.12 divided by 0.2, which is 0.6 meters per second. And then in part 3, we are looking at 1.7 to 1.9. So for this one, we have to look a little more carefully here. So we're looking at this interval right here. So at 1.7 seconds, it looks like we are at 1.14 meters. And at 1.9 seconds, it looks like we are at 1.18. So our displacement is going to be the difference in those two numbers. And then for the time, we're going from 1.7 to 1.9. So this is 0.04 over 0.2, which comes out to 0.2 meters per second. So each one of these is worth 1 point each. Okay, so next thing they want you to do is to graph the velocity of the two carts as a function of time. All right, so here is the graph they give us to work with. All right, so if you go back and look at these markings here, you'll see that they're fairly evenly spaced at the beginning. Looks like we're going about 0.1 meters for every 0.1 seconds, and that lasts all the way up to about 0.7 seconds. Then the marks start to get closer and closer together, and it looks like that lasts for about this time interval here, so to roughly looks like 1.3 seconds or so. And then from here on, it looks like there's a pretty even spacing between the points again. So we have these three intervals. We have a large constant initial speed, and then we have a period of deceleration, and then we have a roughly constant final speed. So we already calculated the initial and final speeds here and here. So those are 1 meter per second and 0.2 meters per second. So we can fill those in for the intervals that I highlighted up above. So we're at, sorry, this is the wrong one. We're at about 1 meter per second for the first 0.7 seconds or so, and then we land at 0.2 meters per second, starting at about 1.3 seconds. And then in between, there's just a period of gradual deceleration. All right, so we get 1 point for really each of these three sections of the graph here. So having a constant velocity here, a constant velocity down here, and then any sort of monotonically decreasing function in this middle region here will give you the third point. All right, so that is part B. Part C asks you to find the speed of glider B immediately after it separates from glider A. So for this one, we're going to have to use conservation of momentum. We know that cart A loses some momentum in this collision because it slows down, and that momentum is going to be gained by glider B. So this is part C. So our equation here is that the momentum of glider A before the collision equals the total momentum after the collision, which is the final momentum of glider A plus the final momentum of glider B. All right, the mass of A is 0.9, and the initial velocity is 1.0, final velocity is 0.2. And then the mass of glider B is 0.6. So we just end up having to solve this equation. And if you go through that, you should find the final velocity of B is 1.2 meters per second. All right, and then that was worth 3 points for that section. Okay, so part 2 of C, they want you to graph the velocity of cart B. So here we know it starts at rest, so it's going to remain at rest until the collision happens at around 0.7 seconds, and then it has a final speed of 1.2, and it reaches that final speed at around 1.3 seconds. And then it's just going to be a smooth increase up to that point. Right, so there should be 3 distinct regions here, and the times for those 3 regions should be the same as in the first graph. So each one of these is again worth 1 point. Okay, and then finally we have a question about the nature of this collision, whether it is elastic or not. So you are given this graph here, which shows the kinetic energy of the first cart during this collision. So you can see it starts with a certain, that's the kinetic energy of the 2-cart system. So we start with a certain amount of kinetic energy here, and then it dips down to some minimum value, and then it comes back up to the same original value. So for part D, question I, is this collision elastic? The answer is yes, simply because the kinetic energy is conserved. Final kinetic energy equals initial, so that means yes, the collision is elastic. So 2 points there, 1 for having the right answer, and 1 for some sort of justification regarding the constant nature of the kinetic energy. Okay, so lastly, briefly explain why there's a minimum in the kinetic energy right here. So when this collision happens, there's a spring between the carts, and when the 2 carts collide, that spring gets compressed, and that means it's going to store potential energy. So that potential energy has to come from somewhere, so the kinetic energy of the carts is going to decrease. So essentially you have this transformation of kinetic energy to spring potential energy, and then back to kinetic energy as the spring relaxes. So since total energy has to be conserved, when the potential energy in the spring goes up, the kinetic energy must go down. So that's why there is a minimum. And 1.0 seconds, that would represent the time when the spring is at maximum compression. All right, so again, for part D, this was 2 points and this was 1 point. So that should cover all 15 points for this problem. Okay, so let's move on to question number 2. This one was actually pretty tricky. This involves a lot of rotation. So to do a bit of review of rotational dynamics here. So this is the first picture that we're given. We have this bar with two masses that's at rest, and then it gets struck by a third mass which strikes it dead center, and then it's going to stick to this bar, and the three masses are going to carry on in the same direction. All right, so question A, part I, asks you to find the total kinetic energy of the system after the collision. So we have to use conservation of momentum here. Say that the initial momentum is equal to the final momentum of the system. The initial momentum is going to be m times VO, which is the momentum of the incoming particle. After the collision, we're going to have all three masses moving as one, so we have a total mass of 3m moving with some final velocity. So that tells us the final velocity is 1/3 of the initial velocity. All right, so our final kinetic energy is going to be 1/2 times the total mass, which is 3m, times the final velocity squared, which is this. So if we multiply everything out here, this should simplify to 1/6 m times v0 squared. All right, so this was worth 3 points. If you had the wrong value for v final here, one tip here is if you write first 1/2 times the total mass times v final squared, this part of the problem here is worth 1 point on its own. So you can at least get some partial credit there. Okay, question 2, find the change in kinetic energy. So we have the final kinetic energy. The change is just going to be that minus the initial kinetic energy. So 1/6 mv0 squared minus the initial kinetic energy, which is just the kinetic energy of the incoming particle. So that's 1/2 mv0 squared. If we do that subtraction, you get minus 1/3 m times v0 squared. Okay, so this is negative because the kinetic energy is decreasing, which it must in any collision like this. Either the kinetic energy will be conserved, in which case delta K will be 0, or delta K will be negative because some kinetic energy will be lost in the collision. All right, and this is 2 points. All right, so the next part, we're now looking at a different collision. So now the particle is going to strike this rod end on rather than dead center. So this one actually gets pretty tricky. We have to remember some things about how to calculate center of mass and how to treat rotation respective to the center of mass. Okay, so this is part B. All right, so first part of B is determine the distance from the left end of the rod to the center of mass of the system. So we can think about this, after the collision has already taken place. So we essentially have mass m here and a mass of 2m here. And our axis is going to be set up like this because we're measuring the distance from the left end of the rod. All right, so the position of the center of mass is going to be the sum of each individual mass times its distance from the origin divided by the total mass. So for the left end of the rod, we have m times 0, and then at the right end, we have 2m at a distance L. This is L here. And then we divide by the total mass, which is 3m. So this gives us 2/3 L as the location of the center of mass. So it's going to be somewhere right around here. All right, part I just wants you to draw an arrow indicating the motion of the center of mass after the collision. Well, all of the motion is in the vertical direction here, so the center of mass is going to continue moving only in the vertical direction after the collision. So this thing may be rotating after the collision, but the center of mass is going to just continue in a straight line. So this object will be rotating around this point after the collision. Okay, so that was worth 1 point, by the way. This one's worth 2. And then part 3, this is also worth 1 point. Determine the speed of the center of mass. This is just a conservation of momentum problem. You can just think about linear momentum, and actually the values are all the same as in part A, so the final velocity is still just going to be 1/3 of v naught. All right, so now here's where things get pretty tricky. Part 4. I want to find the angular speed of this system immediately after the collision. So the angular momentum is going to be conserved here. And you have to remember that there is angular momentum even before the collision, just due to this mass moving in a straight line. So we're going to measure angular momentum with respect to the center of mass. So the initial angular momentum, we have a particle moving in a straight line. So to measure the angular momentum with respect to the center of mass, we take the linear momentum of the object and we multiply by the perpendicular distance from that center of mass. So we found out that the center of mass was 2/3 L away from the left end. So it is 1/3 L away from the line of motion of this incoming mass here. Okay, so that is initial angular momentum. The final angular momentum, now we're going to have a rotating object. So that is going to be the moment of inertia times omega. Okay, so how do we find this? First, we have to find the moment of inertia of this thing around the center of mass. So that is the sum of each individual mass multiplied by its distance from the center of mass squared. So for the left end of the bar, that contributes a moment of inertia equal to m times 2/3 L squared. And then the mass on the right side of the bar contributes 2m times 1/3 L squared. All right, so we have to multiply all of that out, and we should get this to simplify to 2/3 ml squared as our moment of inertia. Okay, so omega is what we are actually solving for here. So now we set our initial angular momentum equal to our final angular momentum. So that's our moment of inertia times omega. And we can cancel m, we can cancel the 3 in the denominator, we can cancel 1 factor of L. So we get, omega equals v naught over 2L. All right, so that whole section there was worth 3 points. And if you got all of that correctly, I would say kudos to you. Okay, so one final part to this problem. Part 5, determine the change in kinetic energy. This one is also pretty tricky. So we need to calculate the initial and final kinetic energy. Initial kinetic energy is just going to be 1/2 m times v naught squared. It's the kinetic energy of the incoming particle. After the collision, we have to be really careful here. There is translational kinetic energy, which is going to be 1/2 times the total mass times V final squared, but there's also rotational kinetic energy. So it's going to be 1/2 I times omega squared. So we've solved for most of these values now. V final was 1/3 V naught. The moment of inertia was 2/3 ml squared, and omega we just found was V naught divided by 2L. So if we work all of this out, this is going to be 1/6 mv squared for the first term, and then notice the L squareds cancel here, so we get mv squared once again. And this is going to be 1/12 mv naught squared. So 1/6 plus 1/12, that's 3/12, which is 1/4 mv naught squared. So the change in kinetic energy, final minus initial, so that is going to be 1/4 minus 1/2, which is minus 1/4 mv naught squared. So those are the final 3 points for this problem. Again, notice change in kinetic energy is negative because this was an inelastic collision, so some of it was lost during the process of the collision. All right, so we have one more to go through. Okay, problem 3 gives us this sort of modified Atwood machine here. So we have 2 blocks stacked on top of each other, and they're connected to a third block via a rope and pulley system. All right, so the first part of this problem just asks you to draw arrows representing the forces acting on the various blocks. So these are each worth a single point each. All right, so part 1, they want the normal force exerted on block 1 by block 2. So that's going to point in this direction. Part 2, they want the friction force exerted by block 1 on block 2. If you read the description for part A, it says the blocks remain at rest, which means the net force on block 1 is 0, so there cannot be any friction force because there would be no other force to counter it. So this one is actually just 0. Okay, so part 3, want the tension exerted on block 2 by the string. The string is certainly going to be under tension, and it's going to pull the block this way. All right, and then we want, so these are block 2, these are block 1. All right, so part 4, we want the normal force exerted on block 2 by the tabletop. That's going to point in this direction. And then finally, we want the friction exerted on block 2 by the tabletop. Now, block 2 is being pulled to the right by a tension force. It's at rest, so the forces must be in equilibrium. So here, there is going to be a friction force between block 2 and the table, and it must point to the left to cancel out the tension force. So we know as a side note that F2 and T, these two forces here, must be equal. And if you analyze the forces on the hanging block, that's also going to be in equilibrium. So this tension force is also going to equal the weight of the hanging block. Okay, so for part B, they want you to find the largest value of M such that these blocks can remain at rest. So that is going to be related to the friction force acting on block 2. So part B is worth 3 points. The first point you get by noting that the maximum friction force, since this is static friction, is going to be mu S2 multiplied by the normal force between block 2 and the table. And that normal force should equal the total weight of these two blocks. All right, so that's sort of the first point that we can get here. The second point we can get is by recognizing that F2, the friction force, is equal to the tension, which is equal to mg, which I pointed out previously. And then we can also say that if m is at its maximum value, that friction force will be what we just calculated in the previous part. All right, and then the third point is just for putting this together and solving for m, so we just cancel the g. So the maximum mass is going to be mu s2 times m1 plus m2. Okay, so part C makes things a little bit more difficult. So now we're going to say that the hanging mass is large enough so that the system actually accelerates. We want to find what is the magnitude of the acceleration. So there are two ways you could do this. If you're a little bit clever, we can do this trick where we sort of change the direction of the forces here. So I'm going to treat all of these masses like a single system, and I've just sort of unbent the string around the pulley, so that will change the direction of this gravitational force. So the only external forces acting on the system are the weight of the hanging mass pulling the system to the right, quote unquote, and then we have our friction force pulling the system to the left. So Newton's second law says that the net force here, mg minus F2, equals mass times acceleration, and that is total mass of the system, m plus m1 plus m2. So this is the equation that we need to work with here. All right, so the friction force, we know that that is going to be the coefficient of friction, which this time is kinetic friction since the system is sliding, times the normal force. And that normal force is still going to be m1 plus m2 times g. So we take this and plug it in up here. All right, so we just divide everything by this expression here, and we get m minus mu k2 times m1 plus m2, all of this times g, divided by the total mass of the entire system is equal to our acceleration. So this should be the expression that we get. All right, so that was part C. That was worth 3 points. And then there's one final part of this problem, part D. So now it says, suppose M is large enough so that the hanging block descends and block 1 starts to slide off of the top of block 2. So we want to find what's the acceleration in that case. All right, so for this one, we cannot treat all 3 blocks as a single system because block 1 and block 2 are not staying together. All right, so first thing we want to do is just find the acceleration of block 1. All right, so let's sort of focus on block 1 here. Imagine here's block 2 with a table underneath it. What are the forces acting on block 1 in the horizontal direction? So it's being accelerated to the right by this friction between block 1 and block 2. And due to Newton's second law, we can say that that is equal to the mass of the block times acceleration. Now this friction force, this is going to be kinetic friction. So that's going to be equal to the coefficient of kinetic friction multiplied by the normal force, which is going to be just m1g. So if we combine these two equations, m1a equals mu k1 times m1g, the masses cancel, and you get the acceleration of block 1 is just mu k1 times g. Right, so that part was worth 2 points. And then finally, the last part here. Find the magnitude A2 and the acceleration of block 2. All right, so for this one, we can sort of use a modified version of the trick I used on the last problem. So now all 3 blocks are not moving together, but these 2 blocks are still moving together. So I can treat the hanging block and block 2 as a single system. So this is M2, this is M. So now what are the external forces? So the weight of the hanging block is still an external force. We still have this friction between block 2 and the table, but now the friction between block 1 and block 2 is an external force that's going to affect the acceleration of block 2 and the hanging block. So again, we write our Newton's second law equation. mg minus F1 minus F2 equals total mass times acceleration. Okay, so we know F1 from the previous part is mu k1 m1g. F2, and this is again kinetic friction, so we had this expression show up in part C. So this is mu k2 times m1 plus m2g. That's the normal force exerted on block 2 by the table. And then that whole thing equals m plus m2 times a. So if we put all this together, we should finally get our answer. M minus mu k1 m1 minus, let me give myself a bit more room here, minus mu k2 m1 plus m2 divided by m plus m2 times g. So this is the answer to the final part here, and this was worth the final 2 points on that problem. Okay, so this problem had a lot going on in it. If you don't remember this trick that I showed you way back in Unit 2 of sort of treating a group of objects as a single system and just looking at the external forces acting on that system and ignoring all of the internal forces like the tensions here, the frictions here, this is a really useful technique that can be used to shortcut some of these problems. So I would highly recommend familiarizing yourself with that again if you've forgotten a little bit. But otherwise, that should cover all of the solutions to these 3 problems. So thank you very much